All right, everybody. You've got a sick kid at home again. So the show's kind of got to go on because we got a deadline in this class with the semester and the AP exam. So we are going to move into heating and cooling curves. You want to take your notes out, probably have a calculator out, make sure you are doing the calculations correctly. And if you need to, pause for a moment so you can get those things out. But heating and cooling curves is kind of a difficult task because there's a lot going on with these problems, and you have to understand what's going on in terms of the substance changing phases from solid to liquid to gas. There are in between phases as well. And then just knowing where you start or stop on these heating and cooling curves can be a little bit tricky as well. So we'll kind of go through some practice problems with you, see where students get tripped up on things, and just understand that not all of the problems are extremely long. Some of them can be short, some of them can be long. It just depends on how much you're trying to figure out in the problem or how much the problem wants you to figure out. So what's going to happen is you're going to have a graph. That graph is going to help you calculate the amount of energy it takes to go from one phase to another for some given substance. Could be water, could be who knows what the material is. Just understand that not every substance is water. So you can't assume that everything boils at 100 and freezes at 0 Celsius. So we can calculate things like how much energy it takes to melt an ice cube, or how much energy it takes to boil water, or even how much energy it takes to melt the ice cube and boil the water all combined together. Each section of this graph has its own equation. There's a lot of repetition in the equations, but it's kind of like you have to do these mini MCAT problems over and over and over again until you reach the destination or temperature you're trying to get to for this problem. Right, so this is what your heating curve is going to look like, or your cooling curve. That's what it's going to look like. Notice that it's divided up into 5 sections. In this section here, where you kind of have like your first diagonal all the way over to the left, this means, or this area is where the substance is in its solid phase. Well, we're just using water as an example here, but again, it could be any substance. And when we're in this section here, we're going to use the equation H is equal to MC delta T. Nothing crazy. When you start to heat up this solid, there's going to become a point where that solid starts to melt. So yeah, like frozen things can be colder than 0 degrees Celsius. All right, so when it's negative 40 degrees outside during a polar vortex, that ice on the surface level is going to match that air temperature. So it's colder than that surface temperature, that 0 degrees. And as you start to heat up, we reach a point where that solid can melt. And when we go from a solid to a liquid phase, we are going to modify this equation. Notice that there's no temperature change anymore. So what we're going to do is we're going to take the mass and we're going to multiply it by this specific heat called the heat of fusion. So it's only 2 things you multiply in this one. The change in temperature isn't happening. So we are just multiplying by the mass times this specific heat. Then once all of the solid has melted, and we just have liquid, we notice that the liquid starts to change temperatures again. And so we have this MCAT equation to find out how much heat it takes to go from the very cold liquid phase to the just about boiling liquid phase. And then once it starts to boil, notice again that the temperature is not increasing. The temperature remains flat. So we're going to take the mass of our substance and multiply it by this other type of specific heat called heat of vaporization, or how much heat it takes to vaporize or turn your liquid into the gas phase. And then once we've heated our liquid sufficiently, we've heated our liquid sufficiently so it's all boiling away, everything is then in the gas phase. And once in the gas phase, it can become hotter than just 100 degrees Celsius. It can get very, 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 very hot once it's in the gas phase. So we see that there's a change in temperature that occurs again. Anytime, this is extremely, extremely, extremely important. Anytime you see change in temperature, like let's say we're starting at -20 and going to 115. When you see this change in temperature, it is only talking about the change in temperature for the section that you are in. It's not asking for the change of temperature of where you started at and where you're trying to end at. So please, please, please pay close attention to that. Otherwise, you're going to get wrong answers very, very, very quickly. Okay, and we'll do an example problem together, of course. So I'll make sure that I'm, reminding you about that. But other than that, it's you have to identify, like, let's say we're starting at a solid and we're just heating it to some point in the liquid phase. There's these 3 sections that we go through, and you'd only have to do 3 calculations for heat and then add those 3 heats together. And sometimes you're just in one section and you have to do only one equation. But all of these equations are basically derived from MC delta T. It's just 2 of these areas are flat. And this isn't only for water, this is for any substance. They will go through these 3 phases: solid, solid changing into liquid or essentially melting, the liquid phase, liquid turning into a gas or boiling, and then the gas phase. The opposite is also true. So this is a heating curve. Well, you might start somewhere up here and go the opposite direction. And when that happens, that is going to be called a cooling curve. So it works the exact same way. The only difference is you should have negative values. This substance is now giving off its heat and it is getting cooler and cooler and cooler. So anytime you're heating something up, you are putting energy into the substance. So that is absorbing that energy. It's endothermic. Anytime you are cooling down, you should always be getting negative values. Okay, so let's look at a heating up example. We start at 0 and we heat the substance all the way up to 100. So for this delta T, it would be my final temperature 100 minus where it started at 0. So my delta T would be 100. But if I was cooling the substance down, then I would be starting at 100 and ending at 0. So this would be my starting temperature up here at 100. This would be my final temperature at 0. So to find the change in T, I would do 0 minus 100, and I'd get a negative value for my T. And this negative value for my T multiplied by a positive value for specific heat and a positive value for the mass would give me a negative number. But what about in the boiling phase or the melting phase where we don't have a delta T? When you're cooling something down, the specific heat that you are given or the heat of fusion that you're given, you make that number negative. So whatever number is they give you for delta H fusion, just put a negative sign in front of it. That means it's cooling down. Same thing for this one. Whatever they give you for the H vaporization or the heat of vaporization, put a negative sign in it. If you are cooling it down, it will keep all of your numbers negative. Or you could just treat the whole thing like a heating curve every single time and then just put a negative in for your final answer. If you're actually cooling it, that works too. Okay, so here are all the equations at all the different spots. It's not really split up well, but here's like my first section. Anytime we have like a diagonal here, it's going to be MC delta T. Anytime we have a flat area, so this would be like our melting area, it's going to be mass times the heat of fusion. And then notice that the masses, these are all going to be the same numbers for mass each time. So that makes the math a little bit simpler, but the delta T's will change and the specific heats, the C's, will change as well. Anyway, yeah, so we got our equations here. When we are heating up the liquid, we're back to a diagonal here. So it's MC delta T. Then when we are boiling something, it's mass times the heat of vaporization. And then when we are heating up the gas or heating up the substance in the gas phase, we've got MC delta T again. We got this just kind of defining again what H fusion, H vaporization stands for. I kind of already did that, or what you need to know about it. So just gonna go through this one quickly. So here we go. Calculate the amount of heat required to completely convert 50 grams of ice at -10 degrees Celsius to steam at 120 degrees Celsius. I'm going to go, okay. Then you're also in some way, shape, or form going to be given this information. But the problem is not necessarily going to give you this graph. You might have to make this and understand where the 5 sections are and what equations go to each section. That is not an easy task the first time around. This is a homework assignment where you probably want to try it on your own as much as you can, not copy off of a classmate, because if you don't know what this graph is supposed to look like and what equation is supposed to go where and where's the heat of fusion and where's the heat of vaporization, things are going to get tricky. But you'll be given some information about where you're starting and where you're ending, and then all the given information, but maybe not the graph. You might have to do that yourself if you need the graph. You do this a whole bunch of times, you kind of know what the graph looks like or what the equations are, no big problem. The important things, the melting point and boiling point, since this is water, the melting point is 0 and the boiling point is 100. Pay attention to these numbers because it's not always water, and your delta T's could get really wonky if you use 0 and 100 for each thing, if we're not always talking about water. And then we've got the heat of fusion value. So that's like the specific heat for the melting. Heat of vaporization, that's like the specific heat for the vaporizing or boiling. And then you've got the specific heats of the solid, liquid, and gas phase, because that's got to be given to you. So here's the first step. Basically, we're going from -10 to 120. So since this is water, we can use this. We're starting here at like -10, and we're going here to 120. So we have to go through all 5 sections of this. 1, 2, 3, 4, 5. So we're starting here at -10. And to get to the end of this phase, we're going to go from -10 to 0. Or to set up that delta T, we're going to go 0 minus -10. And those two negatives together are going to make it a +10 for the delta T. So MC delta T, we said, was the equation for that first section when it's a solid. We'll take the mass times the specific heat of the water when it's in the solid phase and multiply it by the change in temperature. So 0 minus -10. And there's these 2 negatives I was talking about that will become a positive. And so here I've changed that to a +10, and I'm just multiplying these 3 numbers all together. And that's going to give off 1,040 joules of energy. Next, we need to figure out the amount of heat needed to melt the ice. So starting going back here. So now we're going from this spot to this spot in this second area of our heating curve. And so for that section, we're going to do mass times the heat of fusion. So mass is still 50 grams, that didn't change. And then we look up what the heat of fusion is for the given part of the problem and multiply those 2 numbers together, we get 16,700 joules. So that's not too bad. Then we're going to go from this point to this point, because remember, we're trying to get to this area of E. So we're chugging along here, and we're in this third section where we're heating up the liquid. So everything's melted, it's all liquid water in this section. So we're starting here at 0 would be the melting point, and we're going to 100, which would be the boiling point. So that would be our delta T. The mass is still going to be 50, and the specific heat of water is going to be around 4.18. Sometimes the AP exam uses 4.2. You just use whatever they want you to use. So 50 grams, because the mass is not changing. Specific heat of water, 4.18. We've seen that before in a lot of our problems. So this is probably going to be a constant that's just memorized as the course goes on. The final temperature this is ending at was 100, and the starting temperature was 0. So 100 minus 0 makes the math pretty easy. We get 20,900 joules. So we've made it to this point, and now we are going to be boiling that liquid. We've added enough energy to the liquid to get it to start to boil. So the equation we use for this part is mass times the heat of vaporization. The mass still 50 grams, and then from the given information, HVAP is 2,260. Multiply those two numbers together, you get 113,000 joules of energy. And then finally, we want to pay attention because there is an ending temperature that we have. I believe that was 120. So we're starting here at the boiling point, which for water is 100, and we're ending at 120. So 120 minus 100 would give us 20 for our delta T. The mass is still the same, but the specific heat of the gas is going to be different. So 50 times the specific heat of the gas times that change in temperature. It ended at 120 and it's starting at 100. So we're going to get 2000. I'm keeping significant figures. That's why I had to put it in scientific notation. But in reality, you're probably not going to have to worry about significant figures that much. So write it as you wish. Now, we made it to the end, but we still have to add up all of the 5 sections we went through to get the total energy it took to go from that ice cube to a warmed up steam or gas phase of the water. And so that takes 153,640 joules of heat to go from negative 10 degrees Celsius to 120 degrees Celsius. Now, that was like the basic of the problems. And then, the College Board and the writers of the AP exam like to spice it up a little bit. And what they might do instead, let's just go back to, okay. What they might like to do instead is make these joules per mole. So if we started with 50 grams of water, we'd have to convert it to moles and then multiply everything out. You'd still follow the same process, but instead of using 50 grams each time, you would need to use whatever that 50 grams in moles would be. So pay attention to what these units are and make sure that your units match up with the information that you're given. That's one really tricky way that the College Board can kind of throw students off with finding the amount of energy it takes to go from one phase to another. Okay, when we're changing a substance from gas phase all the way down to ice, or it doesn't even have to go to ice. Let's say we're going from gas phase to boiling or gas phase to liquid. We use a cooling curve. It's the exact same thing, but our numbers are negative. Every time we do a calculation like we have here, the numbers should be negative, okay? So if I went from 120 degrees Celsius to negative 10 Celsius, we cooled this from a gas all the way down to an ice cube, it would take the exact same amount of energy, but negative. And then also understand that if it's negative, that means it's exothermic. Or the example problem that we did, it's a positive number for the amount of energy it takes. So that was an endothermic process to get the ice cube to 120 degrees Celsius. But just pay attention. Are you heating things up? Are you cooling things down? You could solve it one way every single time and just plop the negative in front, or keep it a positive number depending on if you're heating it up or cooling it down. And that's pretty much it. So on Schoology, you've got some problems to try. And if you've got any questions, just email me. You're not sure where you're supposed to start or where you're supposed to stop. You can ask me. Some students get confused, like, What if you start from 120 and go to boiling? You're going to have E and D. Or what if you go from boiling to freezing? Then you're going to go D, C, and B. You'll include those three. When it says like go from boiling to freezing, sometimes students just do D and C and don't even worry about B. But if we're going to have everything frozen, we got to do all of B. We don't just stop when we get to B. So that can be a bit confusing if you're going from one of these straight lined phases like boiling or freezing to another phase that's boiling or freezing. Something between B and D students can get confused on. But I think you'll be okay. Again, you've got this as a reference to look through, and you can always ask me questions tomorrow or reference back or email me.